In 1879, Stefan noticed by analyzing the then available experimental data of blackbody radiation published by different people such as Tyndall, Dulong and Petit, Prevost and Denson and others, that the total emissive power of radiant energy was proportional to the fourth power of the absolute temperature of the radiator. He published this conclusion with the assertion that all bodies at the same temperature radiate energy at the same total emissive power. This way, Stefan devised an empirical law for blackbody radiation. However, soon it was realized that different bodies have different total emissive powers even at the same temperature. Due to this reason, the Stefan law was not generally accepted. However, in 1884, Boltzmann used the radiation pressure of Maxwell theory and the second law of thermodynamics and was able to interpret the actual meaning of Stefan's law. With this approach, Boltzmann derived an analytical relation between the total emissive power and the absolute temperature of the radiator in the form I lambda T equals sigma times T raised to the power 4, where sigma is a constant now known as Stefan-Boltzmann constant and T as the absolute temperature of the blackbody radiator. The Boltzmann approach has an important difference with the Stefan's empirical formula. Stefan said that his relation is true for all bodies without regarding to the quality or color of the radiator, whereas Boltzmann related his relation only to a black body. This way, the Stefan-Boltzmann law was finally established in 1884. Now, common experience showed that the total emissive power for ordinary objects is less than the emissive power of a black body. Therefore, the equation of Boltzmann desired for black body can be modified for a general body into the form I lambda equal epsilon times sigma times T raised to the power 4, where epsilon is called emissivity of the object. For a black body, epsilon equals 1, which result back into the original equation of Boltzmann. Stefan-Boltzmann law gives the total emissive power of a black body but say nothing about the energy carried by a component wavelength, their relation to the temperature of the body, and their distribution in the spectrum. This problem was first taken by Michelson in 1887 and was able to derive a theoretical relation for explaining blackbody radiation. However, it could not withstand well with the experimental data and was not considered for long. William Wien in 1893 was able to establish an experimentally verifiable relation between the temperature of the object and the wavelength at which maximum emissive power occurs. He expressed his relation in the form lambda sub max times the absolute temperature of the radiator equals a constant. That is, the product of the absolute temperature and the wavelength at which the emissive power is maximum is always a constant. In other words, the wavelength of maximum emissive power shifts towards the lower value with increasing temperature of the black body. This relation is called Wien's displacement law. 3 years later, in 1896, by treating the field of radiation as a thermodynamic fluid, Wien, in connection with his displacement law, was able to derive another very important formula in the form R lambda times d lambda equals C1 divided by lambda raised to the power 5 times exponent minus C2 divided by lambda T d lambda. When the emissive power obtained from this theoretical formula was plotted against different wavelengths, the shape of the curve agree with the one based on experimental data in the region of shorter wavelengths, but fails completely in the region of longer wavelength. However, this was a very appreciable effort, and based on his valuable work on blackbody radiation, Wien was awarded a Nobel Prize.